Okay, we were given that we had 210 moles of beryllium per 1 mole of fuel. And for this fuel, it was 8% U-233. And then obviously the balance, U-238. Whenever you see an enrichment, and even if you have 2 items, I could have given you a fuel mixture that had 3% uranium-235, 5% uranium-233. Whenever you have that, the balance of that is always going to be uranium-238. Part of that has to do with the fast fission factor. Okay. And then I'm ultimately asking you to find out what is K effective. We know K effective is our 4-factor formula. Okay. Whenever you see this type of problem, the first thing you need to do is set up mole ratios. Okay. So since we have 3 items, we're going to have to establish 3 ratios. And it's not mandatory that you go this way, but by convention, we usually select one item as our common denominator. And again, you could pick anything, but we typically use the smallest item. If you pick something else, in this case, I'm going to pick U-233 because there's only 8% of 1 mole that's U-233, but you could have picked U-238. You could have even picked beryllium as your common denominator. You're still going to get the same answers when you go through, but you're going to find out typically if you do that, you're going to have unwieldy fractions that you're using for your mole ratios going forward. So doing that, if I look at the mole ratio for beryllium, again divided by 233, so that's going to be 210 divided by 0.08, because then this is a percent, but we have to convert it back to a mole. And I had that value come out to be 2625. If we look at the ratio of 238 to 233, that is 0.92 divided by 0.08. And that value was 11.5. And then finally, in 233 to itself, so 0.08, 0.08, and that's 1. So I'm going to move these items up to here. Just so I can keep them handy. Then I have a little bit more room to work over here. So I'm going to go back to my 4-factor formula. Remember again, everything on this side is either fast or epithermal. Therefore, everything on this side is thermal. So just working our way through this, for the fast fission factor, I gave you that in this particular case, which was 1.02. The next thing you had to do was P, which is the resonance escape probability. And that was equal to readable. Okay. So the first thing we need to solve in solving this entire thing is I effective. And I effective is equal to 3.9 times macroscopic cross-section for scattering divided by N to 38. All of this raised to the 0.415 power. And remember, if we go back and look at what's happening with our scattering compared to energy, these are resonances, which when they're high, they can absorb neutrons. So you're replacing this with one effective resonance. And that effective resonance is expressed by this equation. Is this an exact match for what's going on? No, but it's a good representation and we can use it mathematically. So we need to expand on this. So this is 3.9 times. And so since we've asked for the macroscopic cross-section for scattering, we need to include every material that's in the reactor. We also know that this is also equal to N sigma S. Macroscopic, microscopic cross-sections. Both of these are probabilities. This takes into account the number density of the item. So this is going to be N sigma S for beryllium. Of course, we have to use the epithermal value because this is on the left-hand side, plus N 238 sigma S 238 plus N 233 sigma S 233. And again, all of these need to be epithermal values. Of course, this is divided by N 238. Again, we're raising all this to the 0.415. The next thing I'm going to do is go back and divide all these by my common denominator. Remember, we don't have the ability right now to calculate number densities, but we do have the ability to do mole ratios, which is the same as number density ratios. And we've already calculated those, so I can go back and now substitute in. This is 26.25. This is 11.5. This is 1, and this is 11.5. Then I need to go in the back of the book find my value for scattering for each of these epithermal, and for the beryllium, it is 6.11 barns. And these are written in barns so that they cancel out unit-wise. For 238, that number was 8.3. And remember, if you go in the back of the book, you look at the columns for scattering. The first one is absorption thermal. The next one is scattering thermal. And then hopefully they printed the data for the third, which is epithermal scattering. The book was pretty cheap at times. They didn't necessarily print them if it was exactly the same as the thermal value. So for quite a few cases as you're going through, the scattering value for epithermal is going to be exactly the same value as it is for thermal. If you remember back to that plot, this is essentially a straight line with a little bit of droop. This is in general for most materials. There are a few exceptions. If you do the same thing here for 233, that value was 8.2. Already have that. If I do that math, I had this come out to be 3.9 times 1403.7 is raised to the 0.415. When I did that math, this came out to be 78.92. Okay. So if I go back here to my resonance escape probability, this is I effective. So I can plug that in. If we look at this value, it is, if you look at this, it is a reciprocal of that. So this is 1 over this amount. So that means the only thing we need to calculate is squiggle. Squiggle is equal to 2 divided by A plus 2/3. You need to do this for everything that's in your system. So in reality, you should do one for beryllium. You should do one for uranium-233. You should do one for uranium-238. They all have this same equation. But when you substitute in the values, this is going to be a 9. This is going to be a 233. This is going to be a 238. You're going to find out that these values are very small. And basically, you can ignore them. So for squiggle, and this should really be squiggle average, squiggle is essentially squiggle for your moderators. Okay? In this case, we only have 1. When I did this math, that came out to be 0.207. So I can go right now and substitute in here 0.207. And then take e to the minus 1 times this divided by this times this. And the final value I got for P was 0.762. First thing I look at that and I say, does that look reasonable? You know that P has to vary between 0 and 1. You'd like it to be as high as possible because you want to keep K infinity as high as possible. So that looks like a pretty good number. So hopefully you'll have a warm fuzzy that you worked that correctly. Any questions on how we handle that? Okay, I'm going to move that value over to here. Okay. And now I'm going to go back. Now we've had everything that's either fast or epithermal, and I'm going to look at the thermal compositions or contributions. F is the thermal utilization factor. And it's basically looking at the number of neutrons absorbed in the fuel divided by the number of neutrons absorbed in everything. So in this particular case, when we come back over here, we have 2 fuels and we have 1 moderator. So if we go back up here, this is going to be what's going on with my, this is absorption for 233. What's going on with my 238? And again, this is the thermal value. I have to account for everything that's there and the 3 atoms, 2 fuels and 1 moderator. So I'm going to have this all over again. And I really should have put little subscripts here to be consistent. Then I'm going to go back through and divide by our common denominator. I'm going to go back and use our mole ratios. And again, we're doing that because we don't have number density information. So this guy was 1, this guy was 11.5, this guy was 1, this guy was 11.5, and this was 26.5. Then I'm going to go back and fill in the values for absorption for each of these. And again, in each case, although I didn't write it down every time, each of these are the thermal values. Okay. If you go in the back of the book and you look for 233, you'll see that it has listed 2 values. It'll have 540 in F. And then it will have $36 in gamma. So the total is 576 arms. So we're going to go back through and because that is the total absorption. If you go in the back of the book and look for the thermal cross-section for absorption for uranium-238, it's 2.71. You have to put that in both places. And then finally, when you go and look at thermal absorption for beryllium, that value is 0.01. When you do all your math in that, I had this value of F come out to be 0.959. And again, first thing when you do that, you should say, does that look like a good number? And we know, since this is a factor, that F is going to vary between 0 and again 1. You want this number to be as high as you can. It can never be exactly 1 because you're always going to have some kind of moderator in there. So this looks like a very good number, and we're going to save that guy. Anything on what we did there? Okay. final thing we're going to do for our four-factor formula is new, and it's a reproduction factor. And what it's really doing is looking at the number of neutrons created by thermal fission divided by the number of thermal neutrons causing thermal fission. So in the numerator, you're only going to have fuels that cause thermal fission. In this case, we only have the one, which is uranium-233. So that's going to be N-233 times the fission cross-section for 233 times the multiplier that you have for 233. And basically this multiplier it's a rough number that gives you the average number of fast neutrons created per thermal fission. So we had one thermal fissioning fuel, but we have two fuels that are absorbing neutrons. So we're going to have N-233, absorption 233, plus N-238, absorption 238. And again, these are always thermal values. Before I can get going on this, I need to go back and look at my mole ratio. So I'm going to divide everything by my common denominator. This was 1, this was 1, this was 11.5. This value was 530 arms. This value from the table in chapter 4 was 2.5. This overall was 576. And this before was 2.71. So I had that final number come out to be 2.18. And you say to yourself, does that look like a good number? We go back and we expect nu to be greater than 1. We'd like it to be much greater than 1. So if I come back over here, our reproduction factor is 2.18. Now I have everything I need to do to find K infinity. So 1.02, 0.762, 0.969, 2.18. So the final value I got here was 1.62. So does that look good? We know that K infinity is the multiplication factor for an infinite sized reactor, which means it cannot experience leakage. So this value must be equal to or greater than 1, even to potentially be considered. Because if it's 1 or less with leakage, you know you're never going to reach criticality. So in reality, this thing needs to be greater than 1. You'd like this to be as high as possible. That's 1.62. That looks workable. So if we're looking at this for a fuel moderator mixture that we're going to put in a reactor shape, so this looks viable, so we would proceed. And then what we do, which we're going to hopefully cover next week, we're going to take into account neutron current density in order to define what leakage is. We're going to put that in the diffusion equation, and then we're going to come up with the equations that we need to use when we select a shape of a reactor to see if that fuel and moderator mixture will work in that particular shape. So that was this quiz today. I want you to keep, well, like I said, when I have my book, I have paper clipped in my book, page 251, which is example number 1, which is the one for uranium-235. We're continually going to go for the rest of this semester back to have to recalculate K infinities. That's where you do it. So I would earmark that so you could readily get back to that. So I want you to save these values. That's why I put them off to the side. In fact, let me go ahead and put K infinity over here. Because as we continue with additional quizzes, I'm going to give you this same fuel moderator mixture, and we're going to go through and make it go critical. And then we're going to put it in different shaped reactors. We're going to put it in an infinite slab. We're going to put it in a cube. We're going to put it in a rectangular solid. If we get ambitious, we might put it in a sphere. We might put it in a cylinder. And you're going to see how we do that. But the upcoming next 2, 3, 4 quizzes are all going to be based on our beryllium 233 and 238 mixture that you had for your quiz today. Okay. I'm not going to give you a quiz on this due on Monday, but on Monday, I'm going to start to lecture on neutron current density. Neutron current density is J. It is a vector quantity. And just in essence, very quickly, if I look at this whiteboard, and I had this whiteboard go to infinity in the plus x and minus x direction, if I have it go to infinity in the plus y and minus y direction, everything on this side is the plus z side. So if I establish anywhere a little window, and this little window is 1 centimeter by 1 centimeter, I can look at all the neutrons that are running around in the plus z side, and this goes out to infinity, and I could say how many of these are going through this little window. And if I turn this window 90 degrees, so that my window now looks like this, I'm looking at everything that's going in that direction. I'm turning it, so I'm looking at everything that's going in my little window in that direction. This is the neutron current density going in the z minus direction. And the units for this are just like flux. They turned out to be neutrons per square centimeter per second. And we can take this and use this to come up with an expression for leakage. So if this is the only little window in this entire whiteboard that goes to infinity, and there are neutrons going through this, and this is actually perpendicular to that little window, this is a vector. It is the neutron current density. And will use this to determine leakage, and then use that to come up with the diffusion equation. So that's all I'm going to cover on this now. I would like you to read up on the next couple of pages in chapter 9 on neutron current density. Okay. I was going to give you a little bit of a lecture on pure bending, but this other is taking a little bit longer than I want, and I want to give you sufficient time for your exam. So I was going to give you a homework assignment due on Monday for nuclear materials, but I'm going to hold off on that. So I'm not going to give you any quizzes that are due on Monday. So let me go back and I'll any questions on what I did for the other quiz. Okay. Also on Monday, I'm going to pick up pure bending again. So I'm going to go to, where do I want to go? Go back to my email. I'm going to send you the exam, and I want to go over this with you very quickly. Okay, I'm going to send this to you momentarily, but I want you to, before I do this, I want to read this to you. Attached is Reactor Theory exam number 2. And you're going to have 2 choices. You can complete and submit the exam by 3:15 today. If you do that, I will give you an additional 5 points on your exam score. So if you turn it in and you got a 98, then you'll have 103. Otherwise, I expect all the exams to be submitted by Friday of this week at 4 o'clock. And then you will just get your regular score, whatever it is. That way it will leave me the weekend to grade these. And then on Monday, I will send you the solution with your grades. As in the past, for any exam I give you that's virtual, I require the statement that says you've neither given nor received help, and sign it. And again, I'm looking for your registration materials by 4 o'clock on Friday. And I've just sent the exam. So let me go over that with you. Why don't you open that up?
I haven't gotten it yet.
Everybody have the exam?
I have it open.
Okay, I'll read it with you. You have an epithermal flux of 6 times 10 to the 18th neutrons per square centimeter per second that is at a kinetic energy of 0.04 eV. The flux strikes a cube made up of aluminum 27, niobium 93, and nickel 59, as shown below. Each material is sort of an independent slab that is 3 centimeters by 9 centimeters by 9 centimeters that is put together. I want you to consider 2 orientations. One, you're sort of looking down on the top of it. The flux is coming in from the left. Each of those faces is 3 centimeters wide. and each material is 9 centimeters long. If you then rotate that 90 degrees, which you see in the second one, the flux is still coming in, and when you rotate it, the only thing you're going to be able to see is a niobium face. So I'm telling you that our goal is to attenuate or minimize the number of neutrons that our detector measures. And I'm asking you which orientation minimizes the number of neutrons detected after the flux is on for 10 minutes. I'd like for you to justify it. So it's either going to be one orientation or the other. For the second part, as a side benefit, we can use this flux on the niobium 93 to create niobium 94 by neutron activation. What I want to know is how many niobiums 94 do you have after we've had our flux on for the 10 minutes? That is the 100-point exam. Then for extra credit, which is 7 points, I want to know what is alpha for niobium. For niobium, how many collisions does it take to thermalize our initial 0.04 eV neutrons? And then finally, what is the most probable velocity that corresponds to our most probable kinetic energy of 0.04 eV? So all of this is due in 2 hours if you want the extra credit. Is there any questions on any part of the exam? Just to go over this again. Your flux is coming in like this. Your detector's here, which is 100% effective. And I want to know, after it's gone through all these 3 materials, I need to know the total number of neutrons that detector measures. And then I'm going to take this, rotate it 90 degrees. And this is the niobium down here. So what you're seeing now is the niobium face. So this is a niobium, and then just inside that is the nickel. Just side about it. So when I rotate this like this, you're just seeing the niobium here, but just inside that is the nickel. Just behind that is the aluminum, and the flux is coming in this direction. Same 100% detector. How many neutrons are measured there? And we're out for which orientation removes the most number of neutrons.
I got a quick question.
Sure.
Oh, my bad, Dominic. So is the flux going through each of them, or because
Sure.
how we did them before, you had them in front of another?
This flux is uniform, going and hitting it in this orientation, or you rotate it 90 degrees up, and it's going through that. So
I meant like the way we did them before, you had like each element like in front of another, so it would go through, let's say, it would go through the top one first, and then the rest of like that.
Before I might have had something like this, where this was the aluminum, this was the nickel, this was niobium, right?
Yeah. And
here's the detector over here. All I'm doing in this case is I'm taking this, and instead of the flux is still going in that direction, but now I'm taking this and I'm rotating this 90 degrees.
So what you're saying is that it's hitting each layer of the sandwich at the same time, rather than bread, meat, then bread again.
In this direction, it's going through this one, then through this one, then through this one. In this orientation, it's going through this one simultaneously as going through that one, it's simultaneously going through this one. On the exam, this flux is effectively like the second one. This is just rotating it 90 degrees. It's going to be not as much work as you think, because everything has the same cross sections. It has the same number density. The things that are going to change is going to be the lengths involved that it goes through, as well as the cross-sectional area that it's hitting when it goes in. If you ever have a problem on a quiz or exam of mine, that you're lost, you don't know what to do, you can always assume something. Tell me why you're assuming it. If it's wrong, I will take off for that, but that's the only time I will take off if you work the rest of the problem procedurally correct. Okay. Any other questions?
Yeah, I just want to make sure I understand the second part.
Yep.
Is it like columns like we did before, where it first hits the first one, and then the second one, and then the third one?
I mean, for the second part, for activation?
I think she means for the second orientation.
Yeah.
When the flux throws through this one, this dimension is not. This top dimension is 9. This top dimension is 9. This space is 3, but it also goes in that direction 9 centimeters. So when this comes in, it's hitting this space, which is 3 centimeters by 9 centimeters, and it's going 9 centimeters before it hits our detector. This is 9 centimeters. Its space is 3 centimeters.
Sorry, you're blocking the board.
Okay. Remember, each one of these is 3 centimeters by 9 centimeters by 9 centimeters. So if I look at the aluminum, the flux is coming in from this direction. This dimension, the length it's going is 9. If you look at the face of this dimension is 3, but it's 9 in that direction. So the flux is hitting a face that is 3 by 9. It's going through here, measured the detector. This guy, 9 centimeters long, 3 centimeters by 9 centimeters. Going through that, being measured. This one, 9 centimeters long, 3 centimeters, 9 centimeters deep. Flux is going uniformly through that and getting measured by that. In this one, I have rotated it up where it's basically, I'm taking this, rotating it so that the flux is seeing the niobium face first. So you might look at it, you want to disregard this one. In this case, the flux is going in this direction. The only one it sees is the niobium, and the detector is going to be back here. So it's going almost like this problem up here. It's going through the niobium, then the nickel, then the aluminum. Well, we know from before, it doesn't make any difference if I put it the other way, it's still going to be the same number. Just look at that orientation. There's only 2 orientations you have to worry about, because the others are just variations of themselves. So if I took this, flipped it 180 degrees, So that's going through the aluminum. If you're looking at the aluminum phase, so it's going through aluminum, then nickel, then niobium. The answer is going to be the same because we proved that before. Doesn't make any difference which order you put them in. Just think about that a little bit, and hopefully it'll fall into place.
Do we need a temperature here?
You can find the temperature by knowing the kinetic energy.
Okay, thank you.
Any other questions? Okay. Since we had a couple of things answering here, I will send Professor Lance an email saying you're liable to be 10 minutes or so late. So I'll give you to 25 after for the extra credit. If you stop and think about it, it's not that difficult. Yes, you're going to have to find out what the temperature is from the kinetic energy. Okay. And then one of the extra credit I have is what is the velocity associated with that? That's a little bit more complicated to find, but it's not that difficult. Anything else? Okay, I'll look for the exams back by 3:25, and I will send Professor Lance an email right now to let him know you're going to be a couple minutes late. Good luck on that. I will be here tonight till my usual 7 or 8 o'clock. I'll not be in tomorrow, but I will be in Friday afternoon to hopefully collect your spring or winter registrations and all that good stuff. If there's nothing else, I'm going to close out here. I will be back in my office, or you could email me or phone me. Good luck on the exam.